coming here today. My name is Yusuf Morsi, and this is my presentation about the investigation of the tensile strength of 3D printed materials. So first, a little background about ABS plastic. Its full name is acrylonitrile butadiene styrene, and it's a thermoplastic. Typically, it is used in injection molding, and a few examples that are commonly used in the real world are Legos, outlet covers, as you can see here, and also computer keys. As well, it's also a commonly used 3D printed filament. And here are a few mechanical and physical properties of this filament compared with PLA. Just to name a few, the melting temperature of ABS is 204 degrees to 238 degrees Celsius, while with PLA it's 150 degrees to 180 degrees Celsius. The tensile strength of ABS is 46, while with PLA is 50 to 70. So something that's commonly used in the material science world is the structure property process tetrahedron. This basically shows how the structure, properties, performance, processing, and characterization of an object all interrelate. And for this presentation, I mainly focused on the structure. So the structure of ABS mainly consists of three things: acrylonitrile, butadiene, and styrene. So the acrylonitrile it contributes heat resistance to the ABS plastic, while the butadiene gives ABS the trait of being glossy and having a rigidity trait. The styrene gives impact strength and resilience to ABS plastic. And yeah, for the purpose of this study, the effective processing parameters are investigated using the ABS plastic, which I really want to emphasize. So this is the sample geometry modeled. Is the geometry that we use is modeled in accordance to the American Society of Testing Materials D63814. And as you can see here are a bunch of properties of this particular material shape. 15 ABS samples in my experiment were 3D printed in flat, horizontal, and vertical orientations. Since according to research that I have literature review that I looked into, they all have different properties and different tensile strengths. So the print quality that we used was set to solid, which it's important to have the highest density to reduce the air gap between the printed beads, since that has a big effect on tensile strength. And this is a sample that was 3D printed. So sample preparation. First, we have to prepare the material. So we used a few spools of ABS plastic, as seen in the top left, and cut them into around 1 inch pieces. And then soon we realized that the air it gives too much air between the different pieces of ABS plastic. So we decided to cut them into 8 millimeter pieces to fully use our air consumption, to efficiently use our airspace. For mold preparation, first we sanded the mold, as seen on the left. Then after that, the mold was cleaned with the IPA alcohol to ensure that no dirt was in the way when we used Teflon spray, as you can see over here. It was a release agent that we used since it's imperative that the plastic does not stick to the aluminum mold. And after applying the spray, we waited 5 to 10 minutes and then put the 8 millimeter grains of ABS plastic inside the mold. So we had a few challenges. Our first challenge was that the sample was burned and charred due to us not having the top on the first sample, which was 6.1 grams of ABS plastic that was left in the oven for 3 hours at 240 degrees Celsius. And it also oxidized, so we had to figure out a solution for this. So we put a copper plate on top of the sample, and for the exact same time and temperature and same mass that was inside the mold. Now it reduced the charring, but it was not good enough. It was not comparable to the 3D printed samples. So we added an aluminum slab and we increased the mass and decreased the temperature. So we put 6.8 grams of ABS and we left it in the oven for 3 hours at 220 degrees Celsius. Now the mass was excessive. We had a little bit more mass than we needed, but the sample was decent and comparable to the 3D printed specimens. So this is the one that we decided to go with. So for the experimental approach, our steps was 3D printing the samples, as I mentioned earlier, in vertical, horizontal, and flat orientations, as depicted in these images. Then the next step is examinable to fabricate the ASTM D63814 samples to benchmark the properties, and we'll discuss next. And physically testing these samples in accordance to the ASTM D63814 to report the tensile behavior, and we use tensile testing machine for this. So as a basic summary, the plan was print samples, make samples with a mold, and then test the samples. So here's like a visual. This is a visual experimental approach, or an experimental approach. Over on the top left is a CAD design that we soon put inside of our 3D printer, and it produced a 3D printed sample over here. It has to be due to a mistake, such as slippage inside after the sample was applied, and the tightness not being that tight in the clamp. So we use this. This was based on a thesis I researched. This is what we decided to use, which shows how the flat and the side is horizontal, so it's different. It's the same sample, but we call it horizontal. Flat, horizontal, and vertical. And this showed that overall showed that the flatly oriented printed samples had more strain than the other ones, and vertically printed ones had the least strain. And this is due to the way that they were laid out in the 3D printer. The vertically ones were the weakest because they were printed in a different way. Where like in between the layers, it would be the weakest. And here's some data that kind of reflects the graph from the previous slide. It just shows that the flat is more tough than the vertical, and the vertical is the least tough. The sideways is more tough than the vertical, since the vertical was the weakest, as I mentioned earlier, but the flat sample was the most strongest, the most tough. So this is a mold sample. Right now I'm going to get to why we did not do tensile tests on the mold. We were preparing to sand it, and we realized that the sample was too weak for us to even experiment on. This would be a great starting point for a future experiment. But now we know that the processes that we did the mold are not strong enough. We need to some improvements are needed. And as you can see here, there are two samples of the mold that we created that are good. And then the one that broke, as in this image, that passes around. And then, so lessons learned throughout this experiment. Well, one of the lessons we learned, of course, was it's a good idea to accommodate to the 3D printing time, the process duration, since it takes a while. The process design and improvement also takes time, so that's something to also look at before something like this. When preparing the ABS plastic for a mold, it's always better, as I mentioned earlier, to cut it into smaller pieces, just so you can ensure that your airspace is at a minimum. And the application of Teflon spray is also imperative, as you do not want the plastic to stick to the mold. Time management should be a priority. I found it as a priority. It's always like a number one priority in an experiment like this, since time is like money. Experience reflection. So something I want to share is that I felt welcome to the lab. I was given the freedom to use the lab equipment for the project, and I found that something that's good. You didn't get that in high school. I was also given trust to work in the lab. I found that nice to have. Also being invited to activities outside the lab, such as a picnic that we had last week. I found that nice. And I was also given a glimpse of a life of like a master's or a PhD student, that is working inside EML. And I found that as a great experience. So I'd like to thank you for your attention, and if you have any questions, I'd like to answer them. But first, I wanna give these acknowledgements. I really want to thank the EML and all the mentors, Nawin, Dr. Yusuf especially, Nawin, Scott, Richard Lee. I'd also like to give thanks to the Department of Defense, NASA, JPL, SBSU, for giving the funds to the lab, giving us all the opportunity to do things like this. And If you have any questions, we're more than happy to answer.